Hello everyone, my name is Prasad Sridhar. Today I'll be presenting my project evaluating machine learning classifiers for vehicle silhouette identification. This project was part of the IE6318 Data Mining and Analytics course under Dr. Shouyi Wang. Abstract. To give you an overview, this project used the vehicle silhouettes datasets to classify vehicles into four categories, namely Opel, Saab, Bus, and Van. We implemented six classifiers, namely random forest, gradient boosting, SVM, KNN, decision tree, and naive bias. After comprehensive data preprocessing, feature engineering, and hyperparameter tuning, the SVMs performed the best with 82.84%. Introduction. Accurate vehicle classification is crucial for automated traffic management and safety. In 2021, around 127,000 people were injured due to crashes involving red light violations. We use the vehicle silhouettes datasets, which contains 18 numerical features to differentiate between four vehicle classes. The challenge lies in distinguishing the vehicles solely based on the silhouette's attributes using numerical features. The objective was to identify the most effective classifier using evaluation metrics such as accuracy, precision, recall, F1 score, and ROC. Related works. Previous research work has shown potential of machine learning classifiers for vehicle identification. Karimer et al. Used KNN for vehicle classification, while Chen et al. Employed SVMs for classification. Bourget and Bokia assessed multiple models for a case, while Chen 2012 used SVMs to categorize vehicles. Our project builds on these approaches by providing a comprehensive comparison across multiple classifiers. Data exploration and visualization. We implemented six classifiers. The dataset contains 846 samples, each labeled one of the four vehicle classes. The dataset attributes were based on shape features like compactness, circularity, distance, circularity. Statistical attributes like scaled variance along major and minor axes. Also geometric attributes like max length, aspect ratio, and Hollow ratios. We used descriptive statistics to analyze feature distribution, variability, and ensure data consistency. There were no missing values detected. Pair plots and correlation analysis helped us uncover relationship between features, while PCA reduced dimensionality. It also improved visualization and data structure understanding. Here's the PCA plot. Machine learning methods. As I said earlier, we implemented six classifiers, namely SVM, random forest, gradient boosting, KNN, decision tree, and FBS. The objective was to evaluate each classifier's effectiveness in vehicle silhouette identification based on comprehensive metrics. The SVM with RBF kernel constructs optimal hyperplanes for separating complex data. Ensemble models like random forest and gradient boosting aggregate predictions from multiple decision trees. The naive Bayes relies on Bayes' theorem, assumes conditional independence between features. Innovative approaches in feature engineering. The PCA was used for dimensionality reduction while retaining 90% of the dataset's variance. Standard scaler and min scaler normalize the features for consistency, enhancing model training and evaluation. Model training and evaluation. Each classifier was trained on standardized training dataset and evaluated using five-fold cross-validation. Evaluation metrics like accuracy, precision recall, F1 score, ROC were employed to assess classifiers' performance. Hyperparameter tuning. We used grid search for hyperparameter tuning across five folds. For the SVM model, the C and the gamma parameters were optimized to balance model flexibility and regularization. Other models like random forest and gradient tuning had their n estimators and max step parameters optimized. Here's the table showing us the hyperparameter tuning conditions for each classifiers and the values considered for each parameters. Evaluated discriminative ability across classification thresholds. Cohen's kappa and ROC measured the agreement between predictions and true labels. Experimental results. The SVM achieved the highest accuracy of 82.84%, followed by gradient boosting of 76.33% and random forest 75.14%. The knife base served as the baseline model with the lowest accuracy. The hyperparameter tuning ensured each model was tailored for its optimal configurations after the grid search CV. Model accuracy with bar chart. Error bars. This chart visualizes model accuracies with error bars indicating standard deviations from cross validation. The SVM maintained high accuracy consistency while other models showed grade variability. RC curves and precision recall. RC and precision recall curves further emphasize the SVM's superior discrimination between vehicle classes. The curves for radiant boosting and random forest are also displayed strong predictive ability. Here is a table showing us the performance metrics of different classifiers in vehicle silhouette identification. Across all performance metrics, SVM performed the best, while gradient boosting and random forest closely followed through. Here is a bar chart comparing the performance of models. Hypothesis testing. The Cochrane's Q test confirmed significant differences among classifiers with a Q statistic of 198.77. However, McNeema's test with Bonferroni correction didn't reveal significant differences. Confusion matrix. The confusion matrix provides an insight into the classifier's weakness and strengths. The SVM model demonstrated the most accurate predictions across all four classes. Here is a table showcasing us the overall best ranking with SVM ranking 1, gradient boosting 2, random forest 3, decision tree at number 4, KNN number 5, and naive base as number 6. Conclusion. In conclusion, SVM model provides the best classification results for vehicle civets, achieving 82.84% accuracy. The gradient boosting and random forest were reliable alternatives showing consistent performance. Further improvements could include refining feature engineering techniques, expanding dataset size, and exploring deep learning models like CNNs. Acknowledgement. I would like to thank Dr. Shouyi for his guidance throughout this project. References. Here are some of the key references used in the project. Thank you.